Hello everyone. In the lecture series of thermodynamics, our today's topic is standard entropy, which is denoted as S0. Let's start from the expression of entropy for an ideal gas in terms of pressures. We have a lot of expressions, at least two expressions of entropy. S equals to NCV ln T plus NR ln V plus S0, which is an integration constant. On the other hand, in terms of pressure, we have the second expression of entropy for an ideal gas, which is S equals to NCP ln T minus NR ln P plus S0 dash. This is yet another constant merging with the integration constant. So let's begin from this equation, and if the temperature is made constant, in that case this equation has the reduced form, this one. Okay, so we are in state 1 is S1. In that case, since temperature is constant, okay, no problem, let us consider that temperature is T throughout. So it is ln Cp ln T minus NR ln P1, okay, plus constant. On the other hand, S2 equals to NCP ln T again, because temperature is constant, minus NR ln P2 plus that constant. So if this S2 is subtracted with S1, then NCP ln T would be cancelled. Only the left, what will be left? Minus ln P2 plus ln P1, and the constant will also be cancelled. So this would give the result minus NR ln P2 by P1. Okay, so we have arrived up to this. Now, for 1 mole of an ideal gas, this N should have the value 1. So this equation can be written as S2 minus S1 equals to minus R ln P2 by P1. Okay, so we have this equation, S2 minus S1 equals to minus R ln P2 by P1 for 1 mole of an ideal gas. Now, this is representing state 1 and P1 also representing state 1. If this state 1 is assumed to be the standard state where the pressure is 1 atmosphere, and nowadays in the modern days concept by IUPAC it is 1 bar, but where in the old convention we would consider this pressure as 1 atmosphere. No, actually for that there will be no problem. So let's consider this pressure as 1 atmosphere. Okay, and this entropy S1, you should write this as S0. This S0 is not the integration constant. This S0 is standard entropy, which is the entropy at the standard state where the pressure is 1 atmosphere, or according to the modern days IPC instruction, it is 1 bar. Okay, and S2, state 2 would represent any other state other than the standard state. So in that case, S2 should be written as simply S, and P2 should be simply written as P. That means it is any other pressure P and this is any other entropy S. In that case, this equation gets the form S minus S0 equals to, that means S2 has been converted into S. Okay, so we are writing S instead of S2 and S0 instead of S1, and here instead of P2 we are writing P, any pressure, and 1 instead of P1, that is the standard pressure. Okay, and hence it would give the result minus R ln P. So we have the equation S minus S0 equals to minus R ln P, and by rearranging we get S equals to S0 minus R ln P. So this is the equation. Let's plot it. Okay, now we have this expression, so we have to plot this graphically. So how would the curve be looking? It would be a negative exponential curve. So here entropy is expressed as a function of pressure, and hence graphical plot of S against P would give an exponential curve as follows. This is the graphical presentation. So in the x-axis you are plotting pressure in the atmosphere unit. In the y-axis you are plotting entropy S, and at the origin the value where the pressure is 0, the value of entropy is S0, that is the standard entropy. Okay, and this is the negative exponential curve where at the x-axis the point of intersection the pressure is 1 atmosphere, and if P is 1 here, then ln P is 0, then S becomes equal to S0. So here the entropy should be S0. That is the standard entropy. So this is the graphical presentation, provided the temperature throughout is kept constant. Okay, therefore entropy decreases exponentially with increase in pressure at constant temperature. Okay, so that's all for this standard entropy concept. Thank you. Have a nice day.